Hey, everybody, welcome to notes number 2.6, where we are continuing our conversation about probability. Now, in our last lesson, we looked at probability distributions in general. Remember that a probability distribution, especially a discrete one, is just counting our whole number events, our whole number outcomes. Well, the binomial distribution is a type of discrete probability distributions, or they use a discrete random variable in a very specific situation. So if we're going to use this family of probabilities, so think about it like this: or has its own set of rules and has its own set of rules. Now this binomial distribution has its own set of rules. I can use this family or this process anytime there is a fixed number of independent trials. Has to be independent. There are only two possible outcomes for your success, or we can sort our outcomes into only two possible situations. Success is what we want to have happen, versus failure, which is anything else. So as long as I can sort them into those two groups, then I'm eligible for the binomial distribution. Once I've sorted them, the probability of success has a certain percentage. That means the probability of the failure is 1 minus that, just using the complement rule. Then, when we use that random variable to count, X counts the number of successes in our trials. So don't worry, we'll have examples of this. In the probability distribution binomial family, binomial probability distribution, then we have a shortcut to the mean and to the variance. Rather than having to use our one var stats like we did in our lesson, our mean, our mu, is just the total number of trials times that probability of a success. We can find the variance, my sigma squared, by taking my total times the probability of a success times the probability of my failure. And like we learned in our very first unit, because this is sigma squared, if I want the standard deviation, I simply take my variance, whatever I got as sigma squared, and square root it. So that would tell me that the sigma is the square root of n times p times 1 minus p. And that is something you are welcome to add to your formula sheets if it's not already there. So you have to meet all these criteria in order to be considered part of the binomial family. Independent, two possible outcomes, success and failure, and X counts the number of successes. Whole number discrete counting, just like we've talked about over this last lesson or two. If you meet those criteria, then the probability of a certain number of successes, the probability of whatever X we're going to use, is our combinations formula, n choose X, times the probability to my X success times failure to total minus X. This gives you your total successes times my total failures. This just accounts for all the different combinations or ways I can do it. So let's start off our conversation, our examples, just picking out whether or not we have a binomial experiment. Do we fall under that binomial distribution? If it is, specify the values of N, P, and Q. Now, Q is something we haven't mentioned just yet, so let's back up. Some books or some question banks say that 1 minus P can use a placeholder of Q. So anytime you see Q, they're labeling that as the probability of a failure. So just be aware that Q or 1 minus P, those are interchangeable. Either way, they're looking for the complement of my success. So I have a certain surgical procedure has an 85% chance of success. The doctor performs the procedure on 8 patients. The random variable represents the number of successful surgeries. So I need a couple of things. One, I need independence. If I am having surgery on 8 patients, each patient is independent of the next. So we do have independence. My surgery has absolutely no impact on your surgery. The second thing I need to look for is total. Well, no, let me back up. Independent trials. Second thing was success versus failure. Yes, I can have a success. I do have a failure. It either works or it doesn't. And the third thing I need to check for, does X count the successes? The random variable X represents the number of successful surgeries. So I meet all 3 criteria. That means I can sort this into binomial. And it's just a shortcut to finding my probability. So because I am binomial, it wants me to find N, P, and Q. N is my total. How many total surgeries do I have? 8 patients. P represents what's the probability of having a successful surgery. Well, 85% chance of success is 0.85 as a decimal. And last but not least, Q is just that complement, the probability of a failure. So 1 minus my success, probability of failure. Let's try another one of these. A jar contains 5 red marbles, 9 blue marbles, and 6 green marbles. You randomly select 3 marbles from the jar without replacement. The random variable represents the number of red marbles. Okay, remember, I need 3 things. Independence. I need to be able to sort my outcomes into a success versus a failure. And I need X to count the successes. Your first thought might be, yeah, but I've got all these different marbles. This can't be binomial, right? I don't have just 2 outcomes. I can sort it. The random variable represents the number of red marbles. So my success in this case is the number, well, let me back up. My success is red marbles. That is what I'm trying to count or look for. So X is going to count the number of reds. Because all I'm looking for is a red marble, that means the blue and the green are what we're going to say is a failure. So this is still, at least so far, eligible for binomial. The only other thing we have to have is independence. If I want to randomly select 3 marbles from the jar without replacement, was that independent or dependent? If I don't replace the marbles, that makes me a dependent experiment. This is not binomial. You have to meet all of the criteria before you are eligible. You have to meet all the criteria before you are eligible to follow the binomial distribution. Let's look at one more example for this video. Example 2 says that in Pittsburgh, Pennsylvania, about 56% of the days in a year are cloudy. Find the mean, variance, and standard deviation for the number of cloudy days during the month of June. Am I independent? What is my success compared to my failure? What is my X? Well, independence, let's sort through. So I have 56% of the days are cloudy. I want to find all of this for the number of cloudy days during June. So clouds are what I'm looking for. So my X is going to count the number of clouds, or cloudy, I should say, the number of cloudy days in June. That means if it's cloudy, I'm going to consider it a success. Anything else is a failure. And as I'm looking at my days are independent. Today has no impact on tomorrow. So I'm just checking those to make sure, yes, I am binomial. Because I'm binomial, I have a direct shortcut to mean, variance, and standard deviation. My mean, remember that's the one labeled mu, is equal to n times p. So n, how many total days do I have? Not just cloudy, but all days. If I'm in the month of June, June has a total of 30 days. P. Remember, P is the probability of a success. So I'm looking for the probability of being cloudy. The probability of being cloudy, they say I have 56%, so 0.56 as a decimal. That lets me calculate the mean as 30 times 0.56. Let's bring that calculator out. So that 30 times 0.56, 16.8. What does that mean? That means we expect an average of 16.8 days that are cloudy in June. So the average of these distributions, the mean of these distributions, are giving you what we would expect on average for the month. It also asks me for the variance and the standard deviation. The variance has a formula. Remember, variance is sigma squared. And it says I need to take n times p times q, aka 1 minus p. So we know that n is 30. We know that p is 0.56. The only thing we don't have yet is that probability of a failure. 1 minus 0.56 is 0.44. So the variance, 30 times 0.56 times my failure this time, 7. Let's round to 1 decimal, 7.4 variance. Let me pause for just a minute. I need to make us a little bit more room to come back for our standard deviation. All right, y'all, so all I did was move our stuff up a little bit. If I want my standard deviation, that's just sigma. So I need to take and put the square root of my variance. You can do this, just make sure that you include multiple decimals. So 7.392, I want to include all the decimals when I go to take the square root. Or as we've done in the past, at least 3 of my decimals. Meaning on average, there is a variation, a fluctuation, a spread of about 3 days. So let's stop this video here. This was a long introduction to our binomial distribution, but in our next set of videos, we're going to look at actually using it to calculate probabilities.